Okay, so our first talk today is talk by Michael Wibmer, and he will talk about dimension of difference equations.
Yeah, so thanks a lot for the opportunity to speak here. I'll be talking about dimension for systems of algebraic difference equations. Let me just write sigma equations for difference equations. So let me start by just fixing the notation. So K will always be a difference field. So it's just a field with an endomorphism. And to keep the presentation simple, I'll assume that K is algebraically closed and uncountable. Okay, so these assumptions are not really necessary, but just to keep things simple. Okay, so and I'd also like to fix a set of difference polynomials. So they define the system of algebraic difference equation we'll be looking at. So that's as usual the ring of difference polynomials. I'll abbreviate this like this. And so this system, it could be finite, but it could also be infinite.
A sigma field, you mean just sigma is
just an endomorphism.
endomorphism.
A ring endomorphism from K to K. Okay. And so the main question of this talk is so what should be the difference dimension? So what should be the dimension of the system? And so for those people with a background in difference algebra, so that of course there's a classical notion of dimension in difference algebra, and it's given by the difference transcendence degree. However, so this notion, it only captures solutions in different field extensions. And so a lot of people, when they think about difference equations, what they think about is somehow something like recurrence relation. So and then they're really just interested in solutions in sequences, in sequence rings. And so the question I'd like to address here is, so is there a notion of dimension that really measures somehow the size of the solution set in the ring of sequences? And then later on I'll have a precise comparison result between this somehow new or more general notion of dimension and the classical difference transcendence degree. So the idea here for just defining this dimension is that the difference dimension should measure.
What's the point of mentioning that K is uncountable? What's the point of this?
Oh, I'm just saying that so that I can simplify the presentation. So it's not needed, but otherwise the presentation would be more. And at a later point, I can mention how this is used. So the idea is that the difference dimension should measure the degrees of freedom which you have when you write down a solution in the ring of sequences. You should measure the degrees of freedom when, say, specifying a solution of F in the ring of sequences. And so just to be clear how this works, for people who have not seen this, so what do we really mean by a solution in the ring of sequences? Well, so to make sense of a solution, what a solution is of a difference equation, all you need to have is a difference algebra over K. So let me just tell you how the ring of sequences is a difference algebra over K. And this is just by looking at this math. So an element in A gets sent to the sequence sigma to the I applied to a I in N. So this is and this is a morphism of difference rings, where the difference structure on the ring of sequences is given by the shift. The sequence AI. You shift the sequence one step to the left. Okay, so the ring of sequences in K is a difference ring by shifting the sequence one step to the left. And then this map makes it a difference algebra over K. Okay, so in this sense, it makes sense to talk about solutions of a system of difference equations.
So is it pointwise multiplication?
Yeah, it's pointwise multiplication. That's the ring structure, is component-wise. So for example, say if K is constant, just like maybe just the field of complex numbers, a constant difference field, then somehow this is, so this is also just a constant inclusion, and you're doing the usual thing, what you're doing when you're solving recurrence formulas.
Does it satisfy a universal property?
Yeah, so yeah, there actually is some kind of universal property for this, for this ring. It's a little bit, so the ring of sequences is somehow the difference analog of the ring of formal power series for the derivation. Okay, so a solution you can.
So it's not the Hermitz ring because the multiplication.
No, it's not this Hermitz multiplication.
So
it's
your
just,
character is zero.
Just the.
Or what?
No, I'm not assuming characteristic zero.
Okay.
Yeah. So there's no derivation. It's just endomorphism. So there's no problem with the characteristic. So a solution here, we can think of it as a function. A solution in the ring of sequences. Think of it as a function from n times 1 up to n to k. Okay, so the picture is, say something for n equals 3. You think of, so you have this set here, and to specify the solution, you just need to assign a value in K to all of these points. And yeah, so what do we mean by the degrees of freedom here? Well, roughly what we mean is, so say some subset here, if you can choose the value of the function on those points arbitrarily, and then you can still extend this function to a solution, that's what it kind of means for this set to be free. Okay, but so to count degrees of freedom, it makes sense to cut the whole situation at some order, like say I. So to count degrees of freedom, we consider now just the functions from 0 up to I, and 1 to n to k. So I'd like to give a definition of what it means to have a set be free. So and it's essentially what I said. So a subset here is free with respect to f if every function f from t to k can be extended to a solution of f. Okay.
So by the way, from the historic perspective, what did Kohn say about this?
So classically, Kohn they really just focused on solutions in fields, and they have a.
But there is some notion, there must be some notion, must have been.
Difference dimension?
Yeah, yes.
Yes.
So what
Yes. So it's defined through the difference transcendence degree.
And is your thing equivalent?
Yes.
It's just a different way of saying it?
No. Okay. So it is more general somehow. So okay. So Kohn's definition.
With some sort of primality in assumption, right? I mean,
Yeah. So I guess you could say somehow Kohn's definition only applies to irreducible systems, something like that. But so it's a very strong restriction somehow.
And you don't know
have
how to verify it in advance, do you?
Say it again?
You don't know how to check whether Kohn's assumption is satisfied, right?
Yes, that's true.
So
Yeah.
the advantage of your approach is that you don't need to verify anything.
Yes. Okay. But so the main point or the main advantage of my approach is that you have a measure for the size of solutions, which is truly measuring the size of solutions in the ring of sequences, and not the size of solutions in difference fields. So maybe it will become clear through examples. But yeah, I'll give a.
So to clarify, if you're given a system for which the assumptions from Kohn's definition work, will you give the same number or not?
Yes, it will be the same.
Same number.
Yes.
Regardless of what it captures, it's actually the same number as Kohn's number.
But
So-
you haven't defined
So make
the number
okay.
yet.
So yeah. So
But I wanna see, like,
making
what's
an
new about this
so if
way.
so if f is a reflexive prime difference idea, then my definition agrees with Kohn's definition.
Okay.
Okay. But if f is somehow so if the difference idea generated by f is not prime and is also not perfect, nothing, then essentially Kohn's definition does not apply. Okay, so he looks at the perfect closure, and it just gives you something it would give you something different from what I get. Okay, it will become clear in the
And your
example.
thing is more connected to solutions in those cases. The Kohn does something.
Yes,
Okay.
exactly.
Okay, good.
Okay, so that's somehow the naive definition of having freedom in choosing something like initial values for the solution. Okay, so let's look at some examples here of how this works. So for just one variable, so if you look at just one linear difference equation, then so that's the general algebraic formula. But so maybe if you want to think in terms of sequences, it's helpful to just rewrite it as a recurrence formula. So if am plus I plus lambda m minus 1 am plus I minus 1 and so on down to lambda 0 ai equals 0. So you have this for all I. So that's if you want to. That's how you think of the solutions in the ring of sequences for this algebraic difference equation. And so here, if you look at this recurrence, now okay, what do you need to? So which sets are free? So for which values of A do you have a choice? And it's of course just you have the first m values, basically the initial conditions. You can choose them freely, and then everything else is determined. Okay. So in this case, so the set T, they go from 0 to m minus 1. So this set is free, and in fact this is a maximum.
That's a maximal free set.
Yeah, exactly.
But in the definition, any subset of a free set is free, right?
Yes, exactly. Yeah. So that's somehow that's the maximal free set, and somehow you can recover the order of the equation just by looking at maximal free sets.
How is it I or dot dot dot? What is this? No, in the definition. So
in the definition, so here, so this is an I. Yeah.
What is I then? How is it?
I is fixed. So I is say I is greater or equal 1.
Okay.
Is fixed now. So I cut the whole situation here at I. So I only look at degrees of freedom up to order I to be able to count them. In general, typically you'll have infinitely many degrees of freedom.
What if not every function extends, but every but finite?
Yeah, that's a very good point. So let's look at another example. Maybe I'll erase that. Yeah. So
do you always take the set T to be closed downward in the coordinates with the I?
no. It's like in the definition over there. It
Okay.
could be
It's really
could be
odd.
anything.
Okay.
And then, so as Andy kind of already mentioned, you're really mostly just interested in maximal T. And there, I guess you could always find a maximal T which is somehow closed down. Yeah, no, actually no. Yeah. Okay, but let's look at this example. So this one. So again, is kind of helpful to rewrite it in the sequence notation. Okay, so let's try to figure out what kind of degrees of freedom we have here for this system. And now it's clear that, okay, so yi is determined by yi minus 1, and the ci is determined by yi, so there's almost no choice here. So ci is determined by yi, and yi is determined by yi minus 1. So we see, in fact, everything is determined by y0. So can only choose the y0 freely. Let me put this on the quotation mark. So essentially, you think, okay, you can choose the y0 freely. However, the catch here is that not all choices of y0 actually lead to a solution.
0.
So there's some restriction here because of the second equation. So, but not all choices of y0 extend to a solution. So what you need to extend the choice of y0 to an actual solution is that y0 plus n, you get when you iterate this plus 1 here, you get plus n, and you need this to be non-zero for all n. So the y0 needs to be chosen in k but you have to avoid negative integers. Okay, so the moral here is, well, so we should have, I think you'll agree, we should have one degree of freedom. Somehow the y0 is free, but it's not exactly free in the sense of this definition. So maybe this is not the good definition. So maybe I'll just like do this, and I'll replace it with a better definition. Okay.
And you might have multiplied something more complicated, not just avoiding 0. It could have been given by some other recurrence, right?
Yeah.
Yeah. So this. Yeah, so the moral here is that D is, so this set, so 0, 1 should be free okay, but it's not, in the sense of this definition it's not free. So I'll propose a modification of this definition. And the idea is that, yeah, maybe it's just too strong to ask to be able to extend all the choices of a function on T. But like here, you could then you could extend almost all choices of a function on T. So it's just a question how you make precise the meaning of almost all. And yeah, you see, so Zariski open is not what you should be asking for. This is not a Zariski open set. You need to ask for something a little bit more complicated. So that's somehow not an improved definition. So the actual definition, which we'll be using. The set is free if the set of functions from T to K that extend to a solution is generic. And so I'll define what generic means. So the idea is just, okay, if a large set of solution, if a large set of functions on T extends to a solution, then you call that set free. Okay, so what do we mean by generic? So you identify the set of functions on T, you think of it just as a affine space over K, and a subset of K to the M is called generic if its complement is contained in a countable union of proper Zariski closed subsets.
So is this where K uncountable?
Exactly, yeah, exactly. Yeah. So for example, what are the generic subsets of just K? Well, all you can do is remove counter-implementing points. Okay, and so this is exactly what occurred in this example here. And so yeah, so you want to avoid a situation where the empty set is generic. So that's why we haven't covered it.
So Zariski close is just algebraic without difference?
Yeah, just algebra. Yeah. No difference equations in this definition.
Okay. But if I replace generic with Zariski dense, would I get a Coulomb definition or not?
Yeah, okay, so generic sets are Zariski dense.
But not the other way, of course. But maybe for this definition, this would be enough.
So for T, so you're saying so if I put generic here or Zariski dense set, it would be equivalent for T being free. That seems possible.
So meaning that all pathological examples are just of this form.
Yes. So
K to the M.
I don't know. Somehow the underlying result, I guess, is that so there is a projection map from the space of solutions down to the functions here, or to the partial. There's a projection map from the set of all solutions in sequences to the partial solutions, and the image of this projection map is a generic subset of the partial solution, something like So I only define generic for the affine space, but you can also define it for any Zariski closed subset, and then what I just said make sense. But yeah, okay, I think you can, if you would prefer to have to just say any Zariski dense subset here, yeah, that's fine.
So is it, are you proposing to do this because you want to avoid K uncountable?
No, I just want to avoid introducing new term.
So it just looks like
Just look shorter.
Yeah, but so this is, I mean, so this is somehow a stronger statement.
Yes, it's
like
stronger.
okay, you have like so you're talking about almost all, and this somehow gives you like it's really very close to actually being all. Zariski dense would just be like maybe you just have like uncountably many points in the line, so that's not really like, for example here that's not really a free choice somehow for the. If you somehow only have.
But if they would equivalent, right? Then the Zariski dense is easier to prove because it's weaker condition. On the other hand, so weaker condition is always easy to check. Just like from text. Yeah. Okay. Anyway, I just was curious.
Okay.
So this says that X contains a countable intersection of proper open subsets. So countable intersection of open sets, is that, I can't remember, is that G delta or F sigma? But this is something like
G delta.
G delta. So, but this is something like what Hausdorff did for whatever that.
That would be nicer. It's just saying that there's a countable subfield of K, such that all generic points of K to the M over that countable subfield are in X. Yeah. The countable subfield such that all generic points, all algebraically independent points of n tuples over that countable subfield are in X. That's not restatement, isn't it? Yeah. And eventually that countable subfield should come from somehow from the coefficients of F.
Are we applying this definition of generic only to finite sets, right? I mean, that's all we need.
Yeah. So we're trying to count degrees of freedom, and so to count them, I'm just cutting things off at order I,
Right.
and then we are somehow in this finite situation. Yeah. Okay. So now with this definition, now we can really make precise what we mean by the degrees of freedom up to a given order, and so what we mean is the maximal cardinality of any set which is free you look at all sets contained, somehow you look up to order I, and then you look at all sets which are free, and then you look at their maximum cardinality. Okay, so this is the precise definition of what it means to have somehow a free choice for the function, and then it does not extend uniquely, but somehow then on the other points your choice is very restricted. Okay, so that's the precise. So T is free with respect to F. So this is the precise definition of what we mean by degrees of freedom up to order I.
So free with respect to F means that for a generic choice of a function on T, do you think it extends to a solution?
Say it again?
Where free means now that's for a generic function from T to K, that extends to a solution.
Exactly. Yeah. It's exactly this definition. Yeah, not the old definition which was here, which was bad, but this one is the correct one, which gives the kind of the desired result.
But again, you should know exactly what is the Zariski closed sets. They're it depends on the coefficients of F. Right? I mean, in the definition of generic, there's some Zariski closed sets around. Okay?
Yeah.
And they should depend on the coefficients of F. Shouldn't they?
Yeah.
Yeah. So everything depends on F. F is fixed from the very beginning. I'm talking about the dimension of F.
Right.
I'm just saying you should know exactly what is the. You should know exactly what the Zariski closed sets are.
Or like the ones I have to take away here?
Defined over,
Like you want to compute them, or like?
No, defined over the coefficients of F. Something like this. F has coefficients.
Yeah.
Okay, yeah. So
Okay, they are defined over the coefficients.
More explicit.
They can be defined over the, yeah. But yeah, I'm not that interested in computing these exceptional sets or something here. Okay, it's at this point we're just trying to get a nice definition and prove nice results and all.
So
Okay.
for a function that belongs to that set of functions, so that the extent to a solution is generic, it's the whole set of functions that's generic, right? Not a particular function is generic. So
It's the whole set. Yeah, you look at the set.
Right, you
all
look at
those
the whole
that extent.
set, right?
Yeah.
So given one of the functions, is it possible that's defined on T?
Yeah.
That is it possible to have infinitely many extensions?
Yeah, that could happen.
It could happen,
Yeah.
right? Even if it's free, it still could have.
Like you could imagine that at every step,
Yeah,
like you have, like here you have finitely many choices to extend it. Then for the next one, you again have finitely many choices to extend it. Like it's somehow algebraic over the previous one.
fixing
and then
fixing an I.
Yeah. Okay, I is fixed here.
Right.
You make your choice here. Here
Right.
you're fixed. But then to
But
go
then right
on
here,
to extend the function,
Right.
here you may have finitely many choices, and again you may have finitely many choices. So in the end, you actually have infinitely many.
Is the DI plus one thing?
Yeah.
So is DI an increasing sequence?
Yeah. Okay. So that's somehow the intricate question now is to understand this sequence.
Right.
Yeah. And so there's actually not too much we can
Say.
really say about this sequence in this level of generality. Okay. And let me give the definition of the difference dimension now, looking at this sequence.
Okay.
And essentially, so typically this sequence diverges. Yeah, so it doesn't make sense to look at the limit of the DIs. But what you want to look at is to look at DI divided by I plus 1, because you somehow normalize the sequence so that this. So here you're going from 0 to I, so you have I plus 1 elements actually. So if you divide by I plus 1, guarantees that you always between 0, so you normalize it to be between 0 and n in the end. So I mean, we started with a system of difference equations in n variables, so you want the dimension to be between 0 and n.
Right.
Okay, so that's a natural way to normalize sequence. And so somehow to look at this limit here essentially means you look at the density of those points which you were able to choose freely, roughly. Okay. So that's the natural limit to look at. Okay. Yes.
So is di a polynomial in I?
No, not in general. That's one of the key
But
points.
eventually.
No, not even. No, not
for big
eventually.
I, not even
No,
for big I.
yeah. That's a very good
Yeah.
point.
Because that would
Yeah.
be like the
Are
dimension
there simple
polynomial.
examples like the goes?
Yes. I'll get to the example.
Why you don't divide by n to get really a density?
No.
Yeah, I mean, if I divide it by n, I would be between 0 and 1, which then is truly somehow the density. But somehow you want it to be, between 0 and n.
Right.
Right? Like a Frank space of dimension n should have dimension n, So that's why you want it. You don't divide by n, but yeah. Okay, and so it's so really. There's not too much you can say about this sequence.
What is the theorem?
Okay, yeah. So the theorem is really just that this exists. It's not obvious.
Right.
It's not even obvious that this limit exists.
Yeah.
Right? I mean, somehow the sequence is between 0 and n, but it could be very chaotic in principle. Yeah. At this point.
So the way you prove it, does it also give you at least an existence result for algebraic difference equations, for solutions, given initial conditions? This is somehow related to specific initial conditions. So does this give you some sort of existence theorem for initial conditions?
Is it an integer?
Yeah. Okay. It's a very good question. I'll get to that too.
Okay.
So your question is it an existence result? I mean, somehow it's built in. Like if you have your function on the t and it's in the good subset, then it extends to a solution.
So then it is related to what Gleb pointed out. So there is cadence, but maybe for the purpose of existence theorem, it's better to keep it like this, the way you present it.
Yes, I agree. The more functions you can show, they extend the better. Yeah. Okay. Yeah. So this is. So now that we know that this exists, now let me finally define what the dimension is, and this is it. That's the
So
definition.
by the way, you're assuming that for every I, the set of functions that extends is generic. For every I, is that correct? I mean, otherwise, how do you get the whole sequence?
So
The I.
I'm talking about t's. I'm talking about t's here. So I fix the I.
Fix I, right?
And then I can look at all t's.
Yes.
Okay, maybe there's none.
No.
Okay, and then
no,
this
but
would just be zero.
Yeah, but in that definition there, you assume that when t is free, so you take a t which is maximum, all right? Let's say
Yeah.
take a t that's maximum. Then you're assuming, or rather, how that will be generic. That set of functions that depends on I, actually, right?
Yeah, that's what it means. Yeah. So
Right.
if you have a non-empty t, then automatically you get this
right. So when
generic
you
subset.
look at the limit of the sequence di as I goes infinity, you're then having to say that for every I, that set of functions that depend on I are generic.
Well, for every I, there exists a t, and on the t you have automatically you get this
I'm
generic
talking about the whole
subset.
sequence di.
Yeah.
So in order for di to be defined, that set of functions, let's call it whatever, script f sub I,
Okay.
is generic, right?
It's
No,
the,
it's
it's the maximum of
Yeah, it's the
subfields.
maximum, but
It's a
that
different one
maximum,
for each eye.
but that maximum is still generic, right? That set of function is still
That
generic.
shows an independent.
So you're assuming,
It's,
no,
it's different for each eye.
yeah, it's different. So, but then for every eye, you're requiring that things to be
No,
generic.
there's not really any requirement.
No?
It's a definition.
Like, you know, if there's no t, then it's no problem. Then it's just zero.
It's only,
You know?
it's only a definition.
Oh, okay, all right, okay.
I mean, T can be empty.
Yeah.
Yeah, okay, all right.
It's zero.
So some DI could be 0 and some of them 3. Oh, okay, all right.
All right, yeah, so I wanted to give somehow the outline of the proof, because it also gives a little bit more information on what's going on. And so it somehow it boils down to 3 facts. So let me state the first fact. There's a purely somehow algebraic characterization of those sets which are free. So the T is free if and only if somehow you look at the corresponding subset of difference variables.
In the calculus.
Yes.
Explain the definition in 10 minutes, right?
Okay, sure, no problem. Okay. So look at this set. Allen chain is in T, and so we look at this set inside the quotient ring. Now you take the quotient by the difference polynomial ring modulo f. Okay, so this T is free, so you have this property here, if and only if the corresponding set of variables is algebraically independent in this difference algebra defined by f. So as a consequence, you see that di is
So
actually
this is for I sufficiently big then.
this is for every I. This statement is true for every I.
Well, but then F doesn't live in there.
So I'm looking at this. I'm
It's a
looking at this thing here.
Difference polynomial.
Oh,
It's
the
the
whole thing.
difference
This is the whole
polynomial
thing.
ring.
Okay, the whole thing. All right. Oh, okay.
And then
okay,
it follows
sorry,
that,
sorry,
that this di is actually just the dimension of the subalgebra here, generated by the variables where you go up to order I.
Algebraic independent over.
Is algebraically independent in over K.
Does it matter what kind of ring that quotient ring is? Peculiar?
No. So there's no assumption on F. So it's just to get a difference ring, you do the difference idea.
Yeah, but the
That-
notion
that's-
of algebraically independent.
Oh, that makes sense in any K algebra. Algebraic independent. It may not be as nicely behaved
No.
as in field extensions, but the definition makes sense in any K
It's
algebra.
not
Okay.
very so, yeah.
Okay. So in other words, you can also describe this di, the degrees of freedom up to order I, as the dimension of the variety defined by f. So the difference idea generated by f intersects it just with difference polynomials up to order I. So we have a purely algebraic description of these degrees of freedom, which were originally defined just through solutions in sequences. And so, so I guess those with a background in difference algebra can already see the connection now to the difference transcendence degree. And so then fact 2 is that so I said before, there's not too much. So it's a very interesting question to try to understand this sequence of the DDIs. Like, what can you say about it? There's not too much we can say about it, but there's one thing we can say about it, and this is that if you look at the sequence of the DI minus ones, then this is sub-additive. And this means that EI plus EJ is less or equal than EI plus J. Now there's, but it's fairly element. It has a fairly elementary proof, but I'm not gonna go into that right now.
Why do you need to shift it?
Yeah, to explain that, I would need to get into it.
Oh, okay, all right.
Yeah, but you kind of need to. So now there's a general elementary result from analysis. It's called Fekite's subadditivity lemma.
Who's that person?
I'm not sure how to pronounce it. I'm just calling him.
You should be careful what you say.
It's Fekite. I don't know. Okay. 4:25. So it's 20 minutes. Oh no! Oh, it's counting down. Okay. Okay. So the limit. So that's a general fact. If you have a subadditive sequence, then this limit exists, and it actually equals the infimum of the sequence. And so then, as a corollary to this, you also get the same statement for the DIs, and this then actually also it gives you so this slightly stronger result about the infimum here. Then it also gives you at least an upper bound on the dimension. And so I promised to give also the comparison with the classical notion. So if the difference ideal generated by f is prime, so then it is known that this the sequence of the DIs is eventually a polynomial. So then it is of the form d as I plus 1 plus e for d and e integers. And so in that case, d is then equal to this limit. So to the difference dimension. So in that case, it is an integer, but yeah, in general, it need not be an integer. And so let's look at an example. So the most basic example, and it's a very simple equation. I think Ellen called it a stupid equation once, but this is somehow the equation which you need to look at if you. It's the most basic equation to look at if you want to understand the difference somehow between what goes on in different fields and what goes on in sequence rings or just general difference rings. Okay, so if you rewrite this, you get yi times yi plus 1 is 0. So what does it mean? It really just tells you that every second entry of the sequence is 0. So every second entry, you can choose it freely. So what are the degrees of freedom? Well, essentially, yeah, like I said, every second entry you can choose it freely. So the sigma dimension, it will be, it is 1/2, and it kind of makes sense that it is 1/2. And so you get this. You definitely get the rational numbers. You can get rational numbers as the difference dimension of system of algebraic difference equations. And I think it's an interesting open question, which numbers you can get. So for example, you could ask, so if the system F is finite, is it true that the difference dimension is always rational? Okay, I think I'll stop here.
Thank you.
Can you give an example of a subadditive sequence?
This one.
No, concrete example. I mean.
Yeah, I guess if
Well,
you,
of course, I mean the
okay,
one just now. The one just now. Sorry
uh,
about that. The one just now, I guess. Okay, sorry. Well, not quite really.
yeah. So
0, 1, 0, 1, 0, 1, or something.
Right. Like in this case, the I will be like integer part of I plus 1 over 2. And this will give you a nice subadditive sequence.
yeah, it's in general it's an interesting
What's
question
the-
if
what's the
somehow
sequence here?
the sequence of the DIs,
Yeah.
you know, so it's not eventually a polynomial, that's for sure. But
Right.
maybe there's still some, you could still describe it somehow with some, I don't know, some finite data, yeah? Maybe you just need more polynomials on some arithmetic progressions. Who knows?
Can you see everything in different fields?
No, so like this equation, if you look in different fields, all you see is 0. And so Cohn's difference dimension is just going to be 0 here.
Sorry.
And here, so the Drew, somehow, the Drew difference dimension in a ring of sequences is 1/2. Yeah, so that's somehow, okay, so how the standard definition of the difference transcendence degree, loses the information.
So it's kind of the fraction of initial conditions that you can know. It's kind of a
it's somehow
it's kind
the
of a fraction
The
that
idea
you can
is
choose
the
free
it's the
in the whole
fraction.
sequence.
Yeah,
It's kind of a fraction.
yeah. That's somehow the idea.
That's why it's di over I plus
Yeah.
1. I think.
Yeah. And so I have I know what it. So there's a nice somehow explanation or formula of what the difference dimension is for any difference monomial, and it's somehow it's related to a classical invariant from additive combinatorics, additive number theory.
I think maybe you were saying something about this, but I didn't quite hear it. So it's okay. You said you can get any rational number. That's pretty clear.
No, I'm
Can you
actually
get-
I don't even know that.
No.
I don't know that you can get any rational number.
Seems like you could just glue
Yeah, you
together
could just-
examples like that. But maybe I'm
Yeah,
being
it's
too
just
not,
write down a
it's
sequence.
not,
Okay,
it's
it's
not
not
so
so
obvious.
clear.
So what I can get easily is I can get m minus 1 over m. That's what I can get easily. But so if I could get 1 over m, then you could get any rational
I
number.
see. Okay.
But somehow that's what you get easily.
Oh,
Yeah.
okay. I
So
see.
it's a bit.
Uh-huh. All right. But you don't have an example where it's not rational.
No, I would like to see that.
Yeah.
And yeah, so I think it's natural. If you imagine, so to take an f which is an f which is infinite, like a difference idea which is
Yeah.
maybe not finitely generated,
Yeah.
that you could imagine like at every I you're still adding
Yeah.
something tricky in there that you keep it rather chaotic the di's, and then maybe you could get something which is not rational. But yeah, all the examples I looked at, it didn't work. Yeah.
So you're looking at equations defined over a field. Right?
Yeah.
You're not looking at equations defined over the sequence ring itself. So if you were to allow coefficients to come from the sequence ring, you'd probably end up with more complicated. Actually, do you even know that you get that the limit exists in that case? If the coefficients come from the sequence ring?
I don't know. I've never thought about that.
Yeah, so you shoot for it.
So what's the dimension of the Fibonacci sequence?
Well, that's 0.
That's 0.
Yeah, that's 0. Yeah, any somehow linear difference equation.
Even if you have
you have
two.
dimension 0 because somehow the t
Oh, it's all just fixed by 2.
like you're
That's
dividing.
always
You have to
constant
divide
two.
by I plus
Yeah,
1.
You have to
Yeah,
divide
so
by I plus 1.
if you have only
It's
finitely
constant
many
two.
degrees of freedom, you get
zero,
dimension
you
0.
Right.
Yeah.
Okay. Have you tried other sequences from the database? integer sequence.
No, but yeah, but I think like sequences like this, you'll always get dimension 0. You need to have
okay,
somehow
okay,
have somehow a complicated
right.
system,
Yeah,
like
got
something
Yeah, if
something non-linear.
If it stops at some
So
point,
somehow, so it
stationary zone
so
is 0.
something you can show is that if a number is the difference dimension of some system, then it's also the difference dimension of a monomial difference ideal. So somehow it all boils down to a more combinatorial kind of problem.
How does interlace? How does this behave under interlace?
I don't know. So it's I don't know. But so this notion of
You think it should be
dimension,
just a max, maybe?
it's
If you interlace two sequences, one of some
mean,
sigma dimension something, and the other one, could you just?
you're not really just looking at the
Max.
difference dimension of one sequence.
I
Right?
understand,
So
but the sequence could be formed by interlacing, right? I
Yeah.
mean, because that's almost all the time. Well, not all the time. Not all the time. I think Singer has a theorem on that.
I don't know. Okay.
Not the open question. Thank you.
Thank you.